everyone. Sorry I cannot be there today in person, but I'm very happy to share our work on neural certificate and certificate carrying reinforcement learning with a special focus on large-scale autonomy design. So before I step into the neural certificate stuff, I want to give a very quick overview of my lab and what we are working on here at MIT. As the name suggests, we work on is that everything okay?
Can you give me?
Yeah.
Can you speak now?
How about now?
All right. We are connecting to the speaker in the room, and suddenly it went down.
Yeah.
It's good now.
How about now?
Yeah, it's good. Yeah.
Yeah. Okay. In that case, can you, because I hear the echo on my side of my voice.
Yeah, it should be good now, I think.
Let's see. Can you hear me now?
Yeah.
Okay. Okay. All right. Great. So I was saying, my lab is where, as our name suggests, we work on reliable autonomous systems, looking at algorithms and tools for the design analysis and verification of those systems. Now, here I want to give you a very broad overview of what we work on because I won't have time to touch every step we are doing here. But if you have questions or have interest on the other aspects of the work that I won't have time to get to today, just reach out to me, let me know. I can always have a chat or send you some pointers. So on the left-hand side here, what I'm showing is a very broad diagram of computation in autonomous systems. Very rough, nothing trying to say we should separate the computation in such a way, but very broadly, we have sensing and perception parts as the ears and eyes of the autonomous system to perceive the world. Now, the world information will be processed as some sort of a software representation, and this software representation will be sent to computers for computation. Now, this type of computation, of course, include the perception, and then with the perception information, the autonomous system will need to make decisions and plan its trajectories or actions. And ultimately, these planned actions will have to be executed as some concrete control actions or policies on the actuators. So we actually work across different levels of the computation in the autonomy stack on the left. At the very bottom of control, we look at this problem of very large-scale autonomous systems. So this large scale, I will be very specific about what I mean by large scale, but thinking about, at the bottom here, I'm showing some simulation environments that we have been working on, including like a city or a seaport with thousands of robots flying around or driving around to help us deliver packages or with other type of services. We also look at highly dynamical systems like fixed wing airplanes, thinking about if you have watched the movie Top Gun, it's an auto pilot that's replacing Maverick to accomplish very challenging tasks. So these are the stuff I'm going to talk about today, especially the use of neural certificates in these applications. What I won't have time to get to, but we have spent a lot of effort recently, is on the middle layer of decision-making and plan. So here, what we are focusing on is something called the complex tasks, thinking about routing thousands of electrical vehicles in the city of Manhattan here on the left. I'm not sure if you can see my mouth, but on this one here, we have there's tiny yellow dots at the charging stations. So we can ask these vehicles to drive people around and deliver packages while making sure they can always get in charged and they never get too crowded at any of the charging stations. So no congestion allowed. How do we resolve this complex task? Other applications include multiple robots, like multiple manipulators to assemble different objects, and heterogeneous robots finishing complex tasks in the warehouse. So things like this, we specifically focus on how to allow multiple robots to collaborate to accomplish more complex tasks. Here we have involved the use of large language models to help people to seamlessly communicate with robots and at the same time enable some self-reasoning. Unfortunately, I won't have time to talk about that, but very exciting about the research here as well. Hopefully in the future I can tell you more about this part. At the top level of sensing and perception, we are not just so we are not a group of perception. We don't train new perception algorithms, but instead we create these tools for the testing and providing assurance for perception-based planning and control. So our tool will figure out where the bottleneck of your system is, where are the failure cases, and also automatically fix the failures of your entire computational pipeline. And here we have developed tools that can work across different applications like self-driving and airplanes, manipulation, power grids, and a different type of applications on robots. Again, today I will only have time to touch upon the bottom layer of the control here. And let me know if you are interested in other parts or you're particularly interested in any of the detail of the techniques in the testing and assurance or the planning for complex tasks part. Okay, so thinking about multi-agent system in a large scale, what are the difficult problems that would come to your mind at the first? So in our lab, there are a bunch of things that we are very interested in resolving that can be entirely possible for multi-agent robotic systems when they're all navigating to their destinations, but still facing some challenges to use existing methods to solve this approach. So the challenges include a very large fleet of agents. So here I'm not talking about 20 or 50 when people do multi-agent. I'm talking about thousands or tens of thousands of robots simultaneously running in this environment. We could have very high dimensional state and input space. So state could be the dimension of the system is very high, and input could be that the system directly takes sensor input like camera or lidar. How would we even incorporate this type of perception directly in the control and making sure they all work correctly? We could face unknown or imprecise system and environment models. And this is very common. There's no way for us to precisely 100% accurately describe what's happening in the physics of the system and also in the environment when we face different types of uncertainties. And lastly, what we really care about is assurances or guarantees. Given all these challenges, even if we can put up some ad hoc approach, it's very hopeless to provide high-level assurance so people and the whole society can accept this type of robots to run. So when we develop our algorithms, we have this, always have assurance idea in mind, making sure we can provide high level of assurance to the autonomous systems. Now today I will tell you something that we've been working on that is very promising in terms of addressing some of the challenges, and I will also mention the open problems and what could be the interesting directions to go from there. So the work we are building on is called neural certificates, and they are built from this idea called control certificate from control theory. If you took some of the control classes, you should be fairly familiar with one or more of these functions I'm listing here. These functions are not developed by me. These functions pretty much exist anywhere between 100 and 100 to 20 years ago. They're already there, but if you have never heard about those, I can briefly introduce what those functions are. So the left-hand side here, I'm showing something called the Lyapunov function. Lyapunov function is a pseudo-energy function, shows if you find such a function in the vector field, then your trajectories will all converge to the equilibrium point. Now that's a very useful tool to showing that the system is stable and sometimes also can do like reaching to reach the goal it wants to get. In the middle, it's a barrier function. It's getting very popular, especially in the last 10 years, about certifying the safety of the system. So barrier function basically creates a barrier saying this is the safe state, and here are the barriers of safe and unsafe, and my system are not allowed to cross that barrier. If I can show that, then pretty much can show the safety is guaranteed. And the right-hand side is a contraction metric. Contraction metric is a differentiable version of the Lyapunov function, but with that you can track dynamic trajectories instead of just the equilibrium points like the Lyapunov function. So these functions already exist. And for many years, there are so many people working on finding these functions for different types of approaches. Unfortunately, there's still no tool that can just give you this function for any system. It's still considered as a very computational challenging problem, and we don't have a good idea of what is the best function representation that we should use to find these functions. Now, our research is called neural certificate. As you probably can tell from the name, that what we are using as a function representation is a neural network. We are using neural networks to represent these functions as well as the policies. I will tell you exactly how we are doing it, but basically neural certificate is a neural network representation of these control certificate functions. So before I step into the details of neural certificates, I want to give you like overview about what neural certificate can do based on our existing research. We have shown that neural control certificate can help with single agent learning-based control, that the control is certified to be stable or safe or tracking behaviors, dynamic behaviors tightly. And this type of control can be made robust, can be made online, and can be made adaptive to different type of changes in the environment. And I have listed some references here if you're interested in this line of the work. What I'm really excited about is we have shown that neural certificate can really help with the generalization of the learned control policy in a very large fleet of agents. And we have also shown that using neural certificates, we can directly handle high-dimensional state and input spaces when very large dynamic models. We can combine it with reinforcement learning for certificate carrying reinforcement learning. And this is something a lot of people are interested in because now we really do not have to use the model information. It can go completely model free, while our control policies comes with a very nice certificate function for proving this, the desired properties. Sometimes neural certificate can also provide insights on how other uncontrolled agents can react to our autonomous agents. I don't know if I will have time to talk about the last part, but if not, I have the paper here, we can check it out. So in today's talk, I will primarily focus on the second and fourth point I'm going to mention about generalization of the learned controller using neural certificate to a very large fleet of agents, as well as how this neural certificate work with reinforcement learning. So thinking about a multi-agent system, what would be a reasonable architecture for designing a controller? I would say it has to be as decentralized as possible. And at the same time, we should allow the agent to communicate, because ultimately this is a multi-agent system. If they don't talk to each other, it's not possible for them to avoid colliding to each other and also accomplishing the task that are sent to multi-agent systems. So what I'm showing here is a basic setup we have. It's a simple setting where you can see the green dots and the agents are moving to the green dots. When they are getting close, they could talk to each other. That's when there's a line connecting the two agents. That means there is a communication channel that's established. Now they can talk to each other. The line means that they're close enough so they can talk to each other, but if they're too far away, you can see that linkage will break and they will lose the communication. At the same time, you can see the thin lines here. Those are the LiDAR. So the LiDAR here is primarily for understanding what's around in the whole world that cannot communicate with you. For example, the red things are obstacles, and these obstacles could move around, and our agent has no prior knowledge of where the obstacles are, how big the obstacles are, and anything about like obstacle movement information. Now, our requirement is that the agent will reach the destination on time without colliding to the obstacles and without bumping into each other. So I would say a fully decentralized controller in this setting is the promising way to really generalize to different number of agents, to a large number of agents, and also to the changing environment. So this work was presented actually a couple of weeks ago at the conference on robot learning. And the approach we're taking is called graph control barrier function. I have mentioned barrier function, but here is a slightly new concept on top of the traditional control barrier function called graph control barrier function. We think we can treat a multi-agent system just as a graph with vertices and edges. The vertices contain two types of vertices, agents and also the points in the point cloud. And the points are basically the hitting points of the lidar array in the observation. And the edges are defined when two nodes can have a distance that is shorter than r. That means they're the sensing radius. When they're close, they can see each other, they can see the obstacle. But if any of these two nodes are far away, we don't have to concern about their collision avoidance for as of now. And also in practical setting, it will be difficult for the agents that are far away to communicate to each other. Now, if we have this view graph model of a multi-agent system, the graph control barrier function is a scalar function that will take in two types of input and output a scalar value. So the input for each agent would be the edge feature and the node feature. Edge feature basically denotes what are being communicated along the edges, and node features means what that neighbor, that node that is talking to you are. It could be another agent, it could be different types of agent, and it could be just the point in the lidar point, meaning it's an obstacle, it's a point obstacle. Now, the H function as a GCBF control, a graph control barrier function, will take in this type of input and output a scalar. Now, what is interesting here is we want this output value to be positive when it's safe and negative when it's unsafe. Now, clearly, H equals 0 can create a barrier, means my agent can never get across the barrier from positive to negative. Then, if that's true, we know the system is always safe. Of course, this is only a barrier. We have no clue how to enforce this barrier. The third condition I'm showing here basically enforced the safety by saying H should never be negative if it starts in safe, it should never be negative. So how that is enforced? Let's take a look at the first term in the third condition here, H dot. If I say there exists a controller such that H dot is positive, then H will always increase. And in this way, H will never become negative when it's starting to be positive. However, we cannot just let H dot to be positive everywhere, because that means you want the agent to be further and further away from unsafe. But in a lot of the cases, they have to be close to the boundary, right? If two agents are facing each other, they don't have to go all the way to be very far from each other to be safe. They can just bypass each other as long as they don't get too close. That's fine. That means they want to be close to the boundary. So the second term here in that third condition, alpha, is a class K function. Class K function is a monotonically increasing function that will be 0 at 0. But the adding of that alpha class K function here basically says you can be close to the barrier, but you cannot get across the barrier. So those are the three conditions, very intuitive. Now the question is, what can we guarantee and how we find the H function? The first answer is pretty easy because we can establish a theorem saying the existence of a GCBF will guarantee the safety of the multi-agent system from non-colliding initial conditions. However, the next question of finding H will be very difficult. If I ask you to find an H now, what kind of function representation will you choose? I would say almost nothing but neural networks. If we use a polynomial, then how would I even handle the case that my neighbor nodes and edges are changing? I could have one neighbor or like 100 neighbors, depending on what I'm detecting using my lidar, or depending on how many neighbors I have. So there has to be a way to fix this changing neighboring information into a fixed length input. And we have to make use of some advanced encoding architecture here. And as you can see, our CBF is called a control. It's called a graph CBF. Then very naturally, we can use graph neural networks to represent those those GCBF function as well as the control policy. Here we are going to use graph neural network to represent both H and U. And of course you can, so you don't have to choose two neural networks. You can just choose one, but output one for H and one for a scalar value for H and a vector for U. We don't really have to restrict to a particular set of architecture, but using some sort of a graph neural network representation, we can find the GCBF as well as the controller U in the following way. So we are basically just penalizing a single loss function. What is this loss function trying to say? The loss function actually looks very long, but it's very easy to interpret. Now we have three conditions for the graph CBF. What the loss function is saying here is I want these three conditions to hold. Now I have the color encoding of the three terms. Let's just look at the red one. The red one is the first condition says whenever my agent I is safe, the H function's value for agent I should be positive. And in the first term of the loss function, what he's showing here is I'm penalizing when H is negative. And there's a small slack there, not exactly cutting the edge at 0, but give you a little bit of a wiggling room to make the training process a little easier. But other than that, it's just simply penalizing the violation of these three conditions. Of course, you may wonder where the policy being trained. See, in the last condition, we have the H dot term. H dot means the time derivative of H. It means the change of H along the trajectories. Now, trajectories has to be the closed loop trajectories that is controlled by the learned controller. So if we take a deeper look at the H dot and use the chain rule, then you will have the control policy. That's how the control policy is jointly learned. And overall, the architecture of the GCBF representation is the following. We have the node feature, edge features aggregated, and also aggregate all the neighborhood information. This will be through some embedding to a fixed length representation through the attention layer, then go through a very regular graph neural network representation, some multi-layer perceptron representations, and we'll have both H and U. Now, you may wonder, how is the learned GCBF going to look like? With the 4-agent case, you can see that it's actually quite as expected. First of all, the orange dot here is the agent, and the tiny black dot is the endpoint of the LiDAR. We can see that I'm just looking at this agent in the middle here. First of all, for the other agents, it creates a very nice barrier to see what it means by unsafe. In the whole process, if you never see these unsafe barrier come across, then it basically means everything's fine. And for now, it's a safe condition. The other thing we observe here is when the other node is closed, it actually gives us a bigger value on the edge that basically says you have to pay more attention to this edge because this agent is very close. Now, to show some qualitative results, we have trained everything using 16.
Oh, Chuchu, we have a question. Yeah. Oh. I guess she was like pointing at something, but. Oh, yeah, so her mouse is not visible, but in the previous slide, she was pointing at the agent. Yeah.
Yeah, okay, let me come back to the previous.
Yeah.
So here you can see there is one orange dot with all the edges that have numbers pointing to it. This is the plotting of the GCBF in the view of that agent.
Yeah. All right.
Okay, so here, and what I'm showing here is with training with 16 Dubin cars, our resulting controller can theoretically be deployed on arbitrary number of agents. In the first setting here, all the agents have a similar density. Basically, you can see when I put more agents, I also enlarge the space. I enlarge it to the point that on the right-hand side, it's so crowded, it's very difficult to tell there are 1,000 agents running there. But you can see like how well all the agents are navigating to their destination, even if there are a lot of neighbors, and also there are like random obstacles thrown to the environment. There's a line connecting the agent to their destination. So if you see like if they reach the destination, then basically that line will disappear. There will be also a line connecting the two agents, the pair of agents, if they're getting too close. This is an easy setting because this is really a similar training environment as testing, but we have done some stress testing. We have done like increasing density type of setting. Basically, it trains in a very sparse environment. It's like on the left-hand side, you see it's super sparse. There are 16 agents running in this entire blank space, and it's like very it has very few agents, but we just dump more and more agents inside it. Then you can imagine that at some point the agents get so crowded and they cannot move around. And of course, this performance, you can imagine if we don't enlarge the space, the performance will decrease. Now, quantitatively, I can tell you that's exactly what I said. We have different dynamics here. The bottom ones shows the simple setting where we increase the when we keep the same density and ask the agent to travel for similar long length of the distance, then you can see the success rates of the agent training with 16, but test on thousands of agents, keep almost 100% all the time. Now, success means the agents can reach their destinations on time without delay. And on the top here, there will be slightly more challenging environments like increasing density or increasing the or ask the agent to travel much longer if we put more agents in the system. You can see that at some point the performance will start to reduce, especially for the ground vehicles. And in most of those cases, it's not because they be involved in collisions, because it's so crowded that they can't move anymore. So they kind of got all scrambled into the very narrow space, and they get stuck and cannot move anymore. So that's when the performance will decrease, but still much better than the very leading reinforcement learning frameworks like MAPPO and some of our previous versions. We have also tried to dump a lot more obstacles. Now we have obstacles with different sizes and different shape. Here the shape will be more or less the same, but different sizes and moving at different velocity. And we can see that the agent can still have done a great job in terms of moving to their destinations. And quantitatively, we can see that even if we put more agents, and of course this agent with if we put more obstacles in this environment with hundreds of agents, our performance pretty much keep 100% for the success rate when the number of obstacles increase, and each of these obstacles will be a random sample in terms of size and also moving directions and moving speed. While MAPPO in this case will have almost completely failed to accomplish the task. It's fine for reaching the goal, but it couldn't really do anything with the safety. And if I put everything in the simulation environment, how like kind of crowded environments or different type of robots, we can have a nicer visualization of the result. I'm not sure how smooth the video is there. It's supposed to be quite smooth on my side, but I would just want to say the simulation environment itself is a standalone thing that you can also use to visualize and also test the performance of your algorithms. Okay, so with that's my first topic about control barrier functions and how to use graph neural networks to find those functions, as well as control policies to handle a very large amount of agents. With the rest of the time, I don't want to use up all the time, so you won't have time to ask questions. With the rest of the time, I will mention this work about certificate carrying reinforcement learning in a completely model-free setting. This work was presented earlier this year at the Robotics Science and Systems Conference. Now, I take a step back to look at a single agent system. Now, the problem we were solving is pretty much like the control problem we solve for the navigation of robots is pretty much a stabilize avoid problem. Now, stabilize means we want to reach and stay within the goal region, and avoid means we want to avoid entering some unsafe behavior. If I just view this problem as an optimal control problem, what he's solving is the following, as listed as the equation here. We are minimizing some objective. This objective could be like the distance to the goal or something similar to that. We can then such that the safety conditions are always satisfied, where safety is defined using this H function. I kept it as this just to kind of align with the barrier function that we have learned. Of course, as of now, it's only a barrier function, but we don't know how to use it for control policies. Now, if I just look at this problem, my first question is there a Lyapunov function and or a barrier function that we can establish for it? Now, actually, this part is not very surprising because it turns out the policy value function for this optimal control problem itself is both a Lyapunov function and a barrier function. Basically, if our objective L is taking the following form, that is, if the objective L is 0 at the goal and positive everywhere, then the policy value function is shown to be a Lyapunov function. This is quite standard from the optimal control literature. We have also shown that taking the inf of all the H, this is actually a barrier function, and we can use this also as in the policy iteration to create this policy value function that simultaneously being a control barrier function. And this control barrier function is like a barrier function for infinite horizon, meaning it will guarantee the safety forever, because you can see the optimal control problem is defined for an infinite horizon. Now, the standard approach to solve this constrained optimal control problem is to, of course, take Lagrangian, use Lagrangian duality. However, there must be a reason that Lagrangian duality doesn't work for this problem, and I will tell you why. And then we have came up with an approach called the epigraph form. Now, before I talk about why Lagrangian duality won't work, let me briefly tell you what is the epigraph form. Here, I know like I'm running short on time, so I will be relatively fast here. But if you want to see the details, I'm happy to like come back and revisit this part of the technique. Now, if I look at a standard constrained optimization problem, minimize J such that H is smaller than 0. The epigraph form for it says this optimization problem is equivalent to the following: that we minimize some auxiliary variable z, that's a scalar value, such that H is smaller or equal to 0 and J is smaller or equal to z, where z is considered as the upper bound for the J function. So these two are equivalent, and it's very intuitive, right? We just upper bound J and try to optimize that. Upper bound is equivalent to minimize J directly. And we have shown that this middle form of the epigraph form is also equivalent to what on the right, minimizing this Z such that we have solving a min-max problem that is less or equal to 0. And here Z can be considered as a cost budget with a unit of J for satisfying H, while the bottom here, inner loop, is an unconstrained optimization problem. Now, unconstrained optimization problem is really, it's a really ideal case because there will be a ton of approaches we can take to solve that. Then there will be like inner loop solving unconstrained optimization, outer loop we just optimize the inner loop's result over a scalar function, which is also an ideal case because scalar function, we have a lot of different approaches to optimize a scalar function. And that's how we make this a two-stage optimization problem. So using this idea, we have created the epigraph form of the constraint optimal control problem for the stabilize avoid version and show these are equivalent. So I want to briefly talk about why we want to take the epigraph form. The fundamental reason that Lagrangian duality is not working is because the gradient of the Lagrangian duality-based method will scale linearly with lambda, where lambda is the Lagrangian that we are taking. As a consequence, lambda will monotonically increase as long as the constraints are not satisfied, meaning the system is exploring unsafe, and this will cause the optimization process to blow up. While the gradient for the epigraph form will not scale with z, which means even if we are exploring unsafe, z will not blow up, and this entire optimization process will be relatively stable. So here I'm using a very simple case here. You can show it's the same optimization problem. It is the same objective function, but if we vary the value of lambda versus z, you can tell how badly that the objective function is blowing up for the Lagrangian duality approach, while it pretty much stay the same for the epigraph form. On the right-hand side, we can also plot the gradient of both two approaches, and that's fundamentally how epigraph form is working. Now, once we have that, this epigraph form of the constraint optimal control will be solved using the following approach. Let me just directly pull everything here. Basically, we first find the range of z. You can find a very large range and sample a bunch of z's over the range and solve this inner problem, which is unconstrained optimization problem, which we can use any unconstrained reinforcement learning approach to take. Here, what we're doing is the PPO approach. And then we get the value function and the policy for each z, which is auxiliary variable, and we will solve the alter problem by first approximating the value of z using a one-dimensional neural network, and then for the scalar z, we'll just find the optimal z on using some bisection search. So we solve the alter problem to find the optimal z, and the final policy is just the policy with optimal auxiliary value. That means this is the minimum the system can sacrifice to satisfy the safety constraints while making sure it still keep the best performance. Now with that, if we run this on a standard kind of setting of a hopper, and of course we need to stabilize it, so we ask the hopper to jump into that green region. You can see how constrained PPO, which is a Lagrangian duality-based approach, fails versus us can successfully run the hopper into the green region. And what's really exciting about this approach is that we have done this on a fixed wing jet airplane to ask it to travel through a narrow corridor while maintaining a very low altitude. If you have watched the Top Gun movie, this is what Maverick was doing to accomplish the mission. Although this one looks relatively simple, I will show you a more realistic one. Let me tell you a little bit about this model. It's a fixed-wing airplane modeled in Simulink with a 17-dimensional state space and a 4-dimensional input space. And this model was open sourced by the Air Force Research Lab as a challenging problem to develop controller, as well as establishing safety assurances for the pilot. What we have done, the original model, of course, it has a bunch of issues. It was in a Simulink super difficult to run, super slow. We have completely rewrote it into the Python-JAX version to make it much faster in terms of getting the simulation from the model. And we also enhance it from a state-based system into observation-based. We further put a LiDAR on top of the fixed-wing airplane. The 3D LiDAR will navigate around and enable the airplane to be able to tell the obstacles to travel through the challenging environment. Now here's the result. You can see how this fixed-wing airplane is traveling through the very narrow corridor and make it to the end without any even a single scratch to the wall of the mountains. The last piece I want to mention is, you may wonder, I jointly find the control barrier function for safety, the Lyapunov function for stability. The stability was to keep the airplane with a very low altitude, because if you recall from the movie, if the enemy's LiDAR mounted on the top of the mountain, so if they fly too high, they will be detected. They have to maintain a low altitude. Now, even if I have those two functions, ultimately what I'm running is that control policy that I jointly learned. So what can I get of those certificate functions other than a high level of guarantees? Actually, we can even further use those certificate functions as safety filters for any other policy. For example, in this case, what we are mimicking here is when the airplane traveled outside of the canyon, it now meets some mountain area, it has to pull up to abandon that low altitude requirements, because it has to now really fly away from that region. So the airplane will switch to a new policy, and this new policy will do something called ground collision avoidance. And the new policy has no guarantee. It could entirely face some interesting weird failures. What we do is to use the learned control barrier function to create a guaranteed safety set, and also use it as a safety filter to make sure that you can see that on the right-hand side, the unsafe behaviors, original red one will be modified and corrected with minimum modification to make it stay within safe. We can add this type of safety filter on top of any policy, not just the learned ones. You could even have a human pilot sitting in the airplane and flying it. But the safety filter will guarantee is whatever the safety requirement we set, in this case is the ground collision avoidance. We can also create the forward environment set as the safety region. You can see this approach that we have a much larger safety region than the other approaches like MPC. So I want to pause here. There are many other applications of neural certificates ranging all the way from like hardware demonstrations or hybrid systems, power grids, but I think I'd like to pause here. I'd like to pause here for now, just to make sure like we have enough time for questions. Let me come back maybe to the slides here. That's I'll be happy to take any questions if you have.
All right.
So
yeah,
Vinesha, I won't be able to hear the questions. If there's questions, can you repeat those?
Yes, yeah.
Here, great.
Questions?
Have you ever considered system on
I think she has. So the question was, have you considered implementing this on a small remote airplane?
We have hardware results. I didn't show it here. We don't have we have hardware different hardware results, but only for the indoor type of setting. We because we have a motion capturing system that we can use here, and also the safety protocol requirement is very different from indoor versus outdoor. But definitely doing like a outdoor type of testing on the much bigger airplane is definitely our goal to make. I didn't have the videos for the hardware here, but I can point you to the videos if you're interested in those. They're relatively toy examples with quadrotors flying around, and also with a Boston Dynamics spot kind of being the obstacle or being the bad guy that try to sense and capture the agents.
Yes.
So in the first part of the talk, I just wonder how realistic is it to apply the navigation of multiple agents in a real scenario.
Can you repeat the last part?
So the first part of the talk, we saw some simulation results, basically to navigate those agents to the destination, right?
Mm-hmm.
So I just wonder what would be the real application of that, for example, autonomous car or something.
Mm-hmm.
And because I saw in the simulation result, the navigation successful rate seems not 100 because when you increase the number of the agents, right? Have you ever considered what's the consequence in a real scenario if some agents cannot be navigated to a destination?
The question was in the first application. So there was one of the things that you also pointed out is as the number of agents increased, there was a small dip in the performance of safety. And could you elaborate a little bit on why do you think that is, and what is the consequence of it, and how could that be mitigated?
Yeah, so this case, what I was trying to explain is the reason is mainly because of out of distribution test. So in the cases where performance would drop, it's because it's the same environment. You just dump more agents, right? It's like one room. If you have 16, you can still navigate, but if you have 1,000, just so crowded, they cannot move anymore. So that's basically the reason. And we just want to stress test how well our algorithm is. We know there will be an upper limit to it. There will be a finite number of agents you can contain within that space. The other one is like a similar. Now, how to mitigate those? One is like if we can incorporate in realistic setting, if we can incorporate the more diverse training, we don't have to have a huge gap from training to testing. That will be addressed. I think that will be improved a lot. And another thing is, I don't know if in any near future that we will run like thousands of delivery drones simultaneously. I think so far we have pretty much like pushed the performance to the extent that it's if like any companies or any organizations want to run a very large number of agents, I think our approach is already pretty robust to do it.
I see. All right. I have a question on the training itself. So in general, how long does it take to train this?
Yeah, it's actually for the training, it is anywhere between 1 to 5 hours. It's not bad.
All right, and I suppose you for scaling you have to do you have
No,
you don't have to retrain, right?
Yeah, the training is only with 16. It's always only with 16. With more agents, we just do testing. We don't retrain anything. Yeah, testing completely depends on how long it takes to simulate a trajectory of 10,000 robots. So you can do it in parallel. I don't think you can do it in parallel because they have to interact. But yeah, with like 4,000 agents, even just one testing round could take like 20 minutes because there are just simply too many agents in the environment.
Another question is in the first problem, when you consider decentralization and then communication is established when there is proximity.
Yeah.
So could you elaborate a little bit on the exact mechanism? Do the agents know each other's position when they, or they get a signal from administrative?
No, so first of all, there's no central communication at all. Everything is decentralized. And the setting is also very general. Basically, it says when the agents are close enough, and you can define what you mean by close, then they can establish a communication channel. They can they can exchange any information they want. So far, what we have exchanged is only the position and the velocity information when they're close, but you can imagine you can also tell each other what you have seen on your path coming here or other type of historical information. But it's like in practice, it's also similar to, for example, when each of the agent has a Bluetooth, they can only talk to each other when they are very close. There's a range of communication that the agent, if it's larger than that range, they probably won't be able to reliably talk to each other.
I guess then my question was because my understanding is each agent, they measure their own position velocity, right?
Yeah. And position is also relative position.
Oh, so they also measure relative position in relation to what?
In relation to their own destinations.
Oh, and yeah, then I guess since you mentioned something about Bluetooth, is it that the agents, they continuously poll or be on the lookout if anyone is nearby? Because if the agents have just the information about their position, velocity, and the relative position with the goal, how do they know which agent to communicate with?
They don't. So they don't really seek to communicate with anybody. Basically, each of the agents just try to get to their destination. If they see a potential of colliding with other agents or with the obstacle, they decide how to avoid that collision.
Then they see other agents through sensors, so they detect other. I see. Got it. Okay.
And we can completely simplify it by saying, oh, we actually have a ablation study where we disabled all the communication, but only use LiDAR. So that can work too, as long as the other agent can be captured using LiDAR. That can work as well.
I see. Got it.
That it's a single agent gets information from the other agents. And if the number of agents increases, the amount of information that single agent gets in order to make a decision significantly increases. How the model handles that?
I heard this question this time. So first of all, not every agent only directly to their neighbors. They talk to everyone, even with 10,000 if they only have like 28 neighbors of their neighbors. They could directly talk to others through multiple hop, but we are viewing the entire thing in the graph. There will be an upper bound about how many neighbors are communicating. So here, for example, when we try with 16, it's kind of from the assumption that we talk to those 15 at any moment, right? If there's more, then it's not in the training environment. Of course, if you want to have neighbors, you can allow the trainer to have slightly more agents. So that's number one. Two is the whole idea of this graph neural network is the attention layer. It's really telling you which of the neighbors you should pay attention to, how much of attention you should pay it to. That's how it's processing this information in a decentralized way. You can think of you as a person working on this very crowded street. You don't really talk to everyone to know where you should navigate today. You look at what other people's strengths and the possibility of finding a path to get to your destination without other people. That's very close to this type of setting.
So I'll just repeat just to make sure it's communicated clearly. So there is an upper limit on the number of agents that an agent can communicate, even though there are more agents in its proximity. So my understanding is if there are so many agents in very close proximity, their communication network should just be connected network, not necessarily all-to-all connection. So that is
right, exactly.
the condition. And did that answer your question?
Oh, yeah. I was wondering, like, what was the accuracy of the ablation study in which they disconnected the agents? Was there any accuracy or?
Oh, what was the outcome of the ablation study? Was there anything? Yeah, when they muted all the agents, right?
Yeah, we have done the ablation for not like all the cases, but just with like up to 100 agent. Their performance degraded a little bit, but not too bad. I remember it was just like a little bit of a more deadlock that the agent could have than the case when they can talk to each other. But when they don't talk to each other at all, there's a larger chance that they could, trap to each other to a deadlock. They both try to turn to the same direction. Then they kind of face this deadlock without making progresses.
Yes.
Are they using some sort of simulation software, or is it?
I remember they built some of these simulation environments. So the question was, do you use any specific simulation software? Is it open source or?
It's open source. We built this from game engines. What you are saying is basically all in the game. Whatever game you